We are the Hormonal Pathways and Trait Expression Simulator team. We are so excited to be presenting to you all this afternoon. Before we dive into the details, we're just going to go around and do some quick introductions. I'll let Haruta start us off.
I'm Haruta, a rising sophomore at Davidson College.
I'm Nelson, a rising senior at North Carolina Central University.
I'm Vanessa, a rising junior at Duke.
I'm Brandon. I'm a rising sophomore at Davidson College.
I'm Billy. I'm a rising sophomore at Duke.
I'm Charisma. I'm a rising sophomore at Duke. And this is Erin, our team lead, who is a UI UX designer here at Duke as well. So now I'm going to pass it off to Nelson to get us started with the research context of our project.
Okay, so Dr. Nicole Barron is a faculty member in the Department of Biology at Davidson College who studies behavioral neuroendocrinology. She came to us with a research paper and a mathematical model, which she created during her doctoral thesis, that she wanted us to create a website for that would better convey her research.
Yeah, so to get into a little bit more of what that research was and what we were given at the beginning of this program, Dr. Barron created a dynamic state variable model that captured the hormonal effects on an organism's reproductive success at each reproductive cycle. And this model was forward-looking, meaning at each cycle, it outputted optimized values that modeled a organism's reproductive success. So in each cycle, the organism adjusted their hormone levels and tissue sensitivity at different tissues. And this regulation caused the organism to exhibit fitness and express traits of the activated tissues. And ultimately, these processes come together to optimize the organism's reproductive success at each breeding cycle. So given this model and Dr. Barron's goals for the project, we were able to form an objective for the following 10 weeks. And I'm going to pass it over to Billy to talk a little bit about that.
Thank you, Charisma. So after analyzing and digesting our stakeholders' research, we identified a project goal, which was to take the math model that was given to us and build an interactive web application for researchers and students to explore the model and the concepts it conveys. After developing the project goal, the team developed a simple workflow model where we reviewed the research materials, adapted the original model. We built a server and an API, and then we divvied up into three separate teams: the graph visualization team, the tissue simulation team, and the environmental simulation team. Once each team finished their third of the project, we integrated all the features into an informational website. I'm now going to pass it off to Vanessa to talk more about our tech stack.
So now to get into some of the tools that we used throughout the project. So on the front end, we used Svelte as a framework to manage and organize our project. We also used Tailwind CSS to do the majority of our styling. And in the front end is also where the user is able to define parameters, and when the simulations are run, the value of the parameters are passed to the backend. And our backend consists of the mathematical model that we converted from MATLAB into Python, and also a server that we created using Flask. And once the model is done running, the model results will be passed back to the front end through JSON data. And then we use Chart.js and P5Play, both JavaScript libraries, for visualization. So to get a little bit more into what we did with Chart.js and P5Play, our project can be broken into three main components. So the first component is the graphical visualizations done with Chart.js, and this page consists of graphs and shows a more complete view of the model. And next, we have two animations that we created through P5Play. We have a tissue level and environmental level simulation, both which look at the model from different perspectives. And now I'll pass it to Brandon and Billy to get a little bit more in depth about the graphical visualizations.
Now, to move on to the first of our features, we have the graphical visualizations. We have mentioned that we wanted to enable researchers and biology students to understand Dr. Barron's research, which is the main goal for the graphical visualizations. What Dr. Barron envisioned for this page was to have the inputs, which come in the form of sliders, on a website that outputs 5 graphs, as you can see on the screen. Here you can see our multi-run and single run pages. The user can mess around with the inputs to see how the model and the graphs can change so that the user can make inferences on how the represented organism behaves. For the multi-run graph, we essentially run the model multiple times. We will go into more detail in the following demo. As you can see on the left side of the screen, you can see the multi-graph visualization as the top graph. We also have the option to change the multi-line graph to show standard deviations and the median over the specified number of runs that the user chooses. I will now pass it on to Billy to showcase these pages.
Thank you, Brandon. So yeah, our demo starts off at our splash page where users can get excited. It also sets the style and look for our website. The user can then press enter, which takes us into the project's website, our about page. This page includes some of the Code Plus project background, our project goals, and shows the user some cool information about the development team. We can then make our way over to the research page. This page gives a more in-depth background to the research aspects of the project, including some more information about the math model and the more conceptual aspects that researchers might be interested in. From there, we can go over to the single run model. In the single run model, it will guide the user with some recommendation exploration steps. The user can then explore the interactivity of the page by changing input variables and seeing how the graphs update as they change and manipulate those variables. There is also information on every variable in the model through a modal message. This allows the user to better understand and add context to how the variable changes they're making are affecting the model. Now, in the multi-run page, the multi-run page includes a brief introduction and more recommendation exploration steps. The multi-run page has been broken down into two main models, the first of which is a statistics-based visualization, which takes in multiple runs of the model and formats them into the medium and 95% confidence intervals for those runs. The second model shows multiple lines as a chosen variable increments over time. This allows users to see clearly how changing a variable affects the math model. And now I'd like to hand it off to the tissue simulation team.
All right, thanks, Billy. So the goal of the tissue simulation page is to help drive home the relationship between tissue sensitivity and trait expression by allowing users to get a snapshot of how receptor counts and hormone concentrations adjust in each reproductive cycle based on average bird tissue sensitivity. To achieve this goal, we included user-controlled slider inputs, a toggle button for the simulation labels, dynamic buttons, and a legend, as well as opportunities to make visual and numerical comparisons between the simulations. Now here's Charisma with our demo, where she'll go more in depth on some of these new features.
Thanks, Nelson. So as you can see, here we have navigated to our tissue simulation page, and it starts off with a couple of introductory sentences and some guidelines on how to get the most out of this page. If we scroll down, we can see 3 bird buttons, and each of these birds represent a bird of a different tissue sensitivity. So this basically controls how each of the simulations are populated with receptors and hormones. If we scroll down further, we can see the 3 simulations, and these 3 simulations represent a cell from a different tissue that corresponds to a different trait value, which is indicated by the titles of the simulations. So if we want to go ahead and explore what a low tissue sensitivity would look like, we can click on that bird. It starts flapping and it populates the canvases with some receptors and hormones. If we wait a little bit, we can start making some visual comparisons between each of the simulations, between the amount of mRNA produced. We can also make some numerical comparisons between the current rate and the total number of receptors bound within each simulation. If I wanted to take these observations and compare it to a bird with a higher tissue sensitivity, I can go ahead and click on that bird and it repopulates the canvases with new amounts of receptors. There we can see, if we're comparing it to what we just saw before, we can see a lot more mRNA is being produced, and the current rates and total numbers of receptors bound is also increased. So if I wanted to shift gears from looking at just the set values given by the birds, I can navigate to the sliders that we have on the page as well. So I can change the hormone count and also the individual receptor count on each of the simulations. And that way I can compare what 3 receptors looks next to 5 receptors, which looks next to 10 receptors, and make my observations from there. This page does a really great job of emphasizing the tissue level concepts of the paper and why tissue sensitivity is so crucial to reproductive success and trait expression. The simulations show that receptor count really is the limiting factor when it comes to trait expression, because as you can see on the far left, a tissue with only 3 receptors can't really keep up with a tissue with 10 receptors that is constantly varying hormones and creating product. So that is it for our tissue simulation. So I will pass it off to Haruta and Vanessa to talk a little bit about our environmental simulation.
So the goal of the tissue simulation was to show us how an organism's receptor sensitivity affects trait expression. In the environmental simulation, we visualize the actual birds that are changing their receptor sensitivity for every reproductive cycle in real time. The consequence of each bird's individual capability to change their hormone sensitivity is represented by displaying their ability to adapt to external conditions and successfully leaving their offspring. For users, we have 3 birds and sliders to adjust each bird's ability to change hormone sensitivity. Every cycle, the bird chooses whether to express mating or parental effort in the simulation, and we implemented a live table and graph for users to reference how likely a bird is to choose one behavior over the other in the current time frame. We also made the live updating table so that the user can compare which bird is experiencing the most reproductive success by looking at their number of offspring that they produced. Now Vanessa is going to do a demo of the simulation for you guys to see these features in real time.
Yeah, so the page starts off with a brief explanation about the science behind the simulation and also some recommended steps to give you the most optimal experience interacting with the simulation. And then below that, we have 3 sliders representing 3 different birds and their ability to change hormone sensitivity. And those sliders are all set to a default value to create a noticeable change in behavior, but users are free to play around and try different values. So if you look at the simulation right now, the birds are all in a neutral state. But once that run button is clicked, we will start to see that the birds are exhibiting mating behavior. So the other trait that the birds can express is scavenging behavior, which is how we chose to show parental effort. And whichever behavior the bird chooses is based on the mathematical model, and we can explore this below the simulation. So as you scroll down, you will start to see a table and 3 charts. The table shows the number of offspring for each bird, as well as the ratio between parental and mating behavior, and these values get updated as the simulation goes on. So this ratio is the probability that the birds will exhibit one of these 2 behaviors, and it's calculated every reproductive cycle from the model data that is shown in the graphs. So in the graphs, we can see that the red bird with the smaller maximum allowed change in hormone sensitivity takes much longer to reach a plateau than the other 2 birds. This highlights that the ability to change hormone sensitivity affects the traits the birds exhibit, which ultimately affects how quickly these birds can optimize for reproductive success. And that concludes our demos, and we will be going into some of our next steps.
Now that we've wrapped up with our project, we see several next steps for this simulation. First, we want to start considering accessibility of the simulation. The research we're trying to convey here is very complex, so we believe that we must go further than just the tooltip icons that we have to help users better navigate the website. Secondly, we want to implement AI that provides real-time explanations for the graphical visualizations. We already have a model that provides sufficient descriptions for the created charts, so we are currently working to provide it enough computing power so that it can be actually integrated to our website. Finally, we're looking to execute user testing and eventually have our virtual simulation published along with Dr. Barron's research paper.